Hi everyone, welcome to a special edition of Some Good Maths, SGM. I'm your host, Mr. Elcare. Let's get into the maths. Today we're going to be talking about data distributions. Now, if you can remember back to one of the first videos I did, we defined data as facts and stats. So when we say the word data, that's what we mean, facts and stats. And if you distribute something, so distribution of something is where you spread it out. You give it to different places, or you see how it sort of falls in a particular area. So when we're talking about distributions, we're just talking about how those facts and stats are spread out. And so that is our topic for today. And what we find is that data distribution a lot of the time falls into these two categories. So we've got symmetrical data and asymmetrical data. Now I think most of us should be familiar with the word symmetry, which sort of means that something is a bit like a mirror image, isn't it? It's the same on both sides, it's symmetrical. And so asymmetrical means not symmetrical, and that comes from this letter here at the start, that A. That's a prefix which means not or without. And so we see that in other words like anonymous, so that means without name or not name. Atheist, so a theist is someone who would believe in God. An atheist is someone who doesn't believe in God, so not God, without God. One last example, symptomatic. So if you're symptomatic, that means you're showing symptoms of a disease or an infection or something like that. You've got a cough or a cold, sniffly nose, things like that. So asymptomatic means that you're without symptoms. So the A means not or without. And so we've got these distributions which are symmetrical and then not symmetrical. So let's have a look at the not symmetrical ones. So you can have data which is just all jumbled up, it's just a mess, looks a bit like a city sort of skyline. And then we've got other distributions which are sort of skewed a bit. And I'll just put the symmetrical one here so we can compare, but we'll talk about that separately in a minute. So you can see a symmetrical distribution looks nice and mirror image on both sides of that middle point. These asymmetrical ones, they have sort of been pushed or skewed to one side. So we can see here this has been spread out more to the left, just like you grabbed that tail of the graph there and pulled it out. And then over here we've pulled the tail to the right, so that's been skewed to the right. And like I said, that one is just a jumble. Over here we've got our symmetrical distribution, and this is also called a normal distribution because we find that a lot of normally occurring phenomenon, so normally occurring things, fall into this sort of model if we graph them, if we collect data from them in a survey or something like that. So things like people's heights, if you were to measure everyone's height in your class or in your street or in your city, you would find that the heights fit this sort of pattern. We have most people around this middle sort of mark, and whatever that is, it might be like 160, 170 centimetres or something. And then we've got people at either end who are a fair bit shorter than that normal part or a fair bit taller. But we have that bulk of people in the middle. And that's true of other things too, like if we were to graph the test results from your last maths test, it would again fit this bell curve sort of model. We've got a lot of people around the middle, and then we've got people at either end who did particularly well or particularly poorly, and you know where you sit. But then over here we've got these asymmetrical distributions. I'll just put this little bit in here too, just to say this is called a bell curve sometimes, just because it looks a bit like one of those old-fashioned bells. So that's called a bell curve or a normal distribution. They're sort of the two words we use to describe that. All right, so what we'd like to do now is just have a look at these curves in a little bit more detail, thinking about mean, median, and mode, and where they exist on these graphs. So if this is our first one, this is our normal distribution, it's our symmetrical distribution, then what we find in these distributions is that the mean and the median and the mode are all in the same place. So we've got mean being the same as the median, being the same as the mode. And if you've forgotten what mean, median and mode are, then I'd recommend you go back and watch that Maths Antics video, mean, median, mode. That gives a really good visual explanation of what these things are. But just to summarize, the mode is the highest occurring data value, so it's the most frequent data value. And so we can see here, this middle column, that is our most frequent column. That's got the most data points in it. So that's our mode. The median is the point where we have 50% of data on either side of it. So because this is a symmetrical distribution, we've got 50% of our data on that side, and then we've got 50% of our data on that side. So that also serves as our median. And for our mean, that was where if we have the raw data, so if in this case we were to actually write out the raw numbers, so in this case we might have might be 100, and remember this represents like 100 to 110, this first box, and this side part here is our frequency. So this is saying there was maybe, it's hard to read off there, maybe about six data values which are in the 100 to 110 range. So I'm just making up data values here, but it might have been something like 101, 103, 105, 109, how many is that? One more, do another 109. So they might have been the actual raw data numbers from that first column. And so we could go through, if we had the actual data, and write out all the raw data numbers for everything there. And what the mean is saying is, where is the balance point for those numbers? Think of it maybe a bit like a set of scales, where if we bring them all to the same level, what is that level? And that's our mean. So at this end, we're looking down here at 100, but up the other end, if we skip right to the end of our data, we've got numbers like 199 and 200. And so you can see, if you were to bring those back, you've got 200 and 100, that would come back to 150. 199 also would cancel out with some numbers and bring that back. And in a symmetrical distribution, they essentially all cancel out and come back to this middle point here, which would be about 150. That would be our mean, median, and mode in this symmetrical distribution. So let's see how that compares with some asymmetrical distributions. All right, so here we have an asymmetrical distribution. And you can see from that text up the top there, it's skewed to the right. And we want to talk about why it's skewed to the right and not to the left. I know for myself, when I look at it, I naturally tend to focus on the higher part there, so these higher columns, and I think, well, it looks like it's actually on the left. Like that's sort of where my eye line is focusing. I would say, oh yeah, that's skewed to the left. But it's not. From a mathematical perspective, this is skewed to the right. And so let's just spend a minute unpacking why that is. To help us, we're going to get our good friend Wally the whale. So Wally the whale is going to help us understand why this is skewed to the right. There's a little saying which you might want to memorize. It says, grab the whale by the tail. So we're going to grab Wally by the tail, and that helps us remember which way it's skewed. We're looking for the tail of the data. So Wally's head sort of represents those high columns up there, and here's his tail down here. So wherever his tail is, that is the direction of the skew. So Wally's tail is over here on the right, so this data is skewed to the right. Now the reason it's skewed to the right is because it's to do with how the mean has moved position from the median. If you remember back to our symmetrical data, we spoke about how our mean, median, and mode were all in the same spot. They were all here lined up in the middle together. But for this asymmetrical data, things have changed. Because the data has been spread out differently, we don't have them all lined up in the same spot anymore. So the median, remember, represents the 50% mark of the data. So in a symmetrical one, it's pretty easy to see. Just, okay, 100, 200, come halfway, and there's our line of symmetry where it mirror images on both sides. But over here, 10 and 60, so maybe somewhere around there would be the middle point. we don't have the same amount of data values on this side as we do on this side. Remember, this is frequency over here. This column represents frequency. So you can see if we have our middle point here, we've got a bit under 10 data values there, then suddenly we've got 40 and 50, so we're up to almost 100 data values, just those first three columns. And then, 25 and 20, we're up almost near 150 on that side. Over here, we've got figures like, even if we count them as tens, 10, 20, 30, 50. So 150 versus 50, that's not our middle point of the data. So the median is where it's 50-50. So we need to keep shifting along, and our median is going to be maybe somewhere like back about here. And so that represents, okay, we've got 50% of our data values here and 50% of our data values here. So that would be our median. Now the mean, remember you've got to think about the mean in terms of the raw data. If we wrote all these numbers out again as raw data numbers and then tried to bring them to a balance point, where is that balance point? And the mean gets affected more by these raw data numbers. So because we've got some really high numbers, even though there's not many of them, so we've only got 10, 20, maybe 30 higher numbers compared to this 150 lower numbers. But because they are higher numbers, that will drag the mean across to the right. It's going to pull the mean across this direction. And we might find, I haven't calculated this, I'm just making it up. But we might find that the mean sits somewhere maybe about there. So that might be our mean. And so that is why we say the data is skewed to the right, because the mean has been pulled across to the right. Whereas it used to be on the same point as the median, now it's been shifted across to the right. Now the same is true of shifting it to the left, and we'll get our good mate Wally to help us again. So here's Wally, grab the whale by the tail. And so thinking about where Wally's tail is, this data has been skewed to the left. And so the same thing has happened again. We've got our median line, which has been shifted to somewhere around there, because that represents the 50% mark of our data. And our mean has been pulled across to the left by these low numbers here. So these low numbers, even though there's not many of them, they've skewed the data to the left. And maybe I should just do an example to really highlight this. If we were trying to work out the mean, so the average of these numbers, let's say we'll have 1, 2, 2, 4, 4. Let's do that. So 1, 2, 3, 4, 5, 6 numbers. So to work out the mean, remember this is our symbol for the mean, that little Greek mu. So we'd add them all together. 1 plus 2 is 3, plus 2 is 5, plus 4 plus 4 plus 4. So 5 plus 12 is 17. And we're going to divide that by 6 numbers. So that equals about 2.83. But if we add on 150, then that really skews the data because it pulls that data out, and we end up with a mean closer to 23. So even though there's only one of these really large data points, it really pulls that mean out. And that's what's happening here with the data. Even though we've only got a few of these really small numbers, it pulls that mean across, and then that's why we say it's skewed to the left, because it's pulling it to the left. So look, that's it for today. And remember, no matter how bad things get in the classroom, there's always good maths out there to be done. Thanks, see you next time.